Okay, let's get started. So welcome back, everyone. So today we're going to talk about parallelism. And remember, in the last week, we introduced how to make a single GPU go fast by writing kernels. And we really looked inside its GPU. And this week, we're going to talk about how to leverage multiple GPUs to make your code go even faster. So the picture you should have in your head is something like this. So for the last week, we focused on one of these boxes where you have your GPU. Remember, you have your high bandwidth memory, HBM, L2 cache, L1 cache, registers, and a bunch of streaming multiprocessors. So now the picture gets extended because instead of having one GPU, you might have 4, you might have 1,000 GPUs, and those are going to be connected. And I'll talk later about how those GPUs are going to get connected. And then you're going to have to figure out how to leverage all of this compute to train models. So in both cases, meaning both in the single GPU case and in the multi-GPU case, as we'll talk about today, the situation is kind of similar if you zoom out, which is that the compute, the arithmetic logic units, the tensor cores, so on, is far away from your data. And far away for a single GPU means all the way over here in HBM. And now, if you have multi-GPUs, the thing that you need here might be all the way on a different GPU. And you're going to have to shuffle that over somehow. But the same principles are going to be the same because the game is to orchestrate the computation to try to avoid data transfer bottlenecks. It's very easy to use a ton of GPUs, but it's hard to use them effectively. So taking a little bit of liberty, we can think about the generalized hierarchy where at the sort of local level next to the SMs is a single node, single GPU where you have an L1 cache shared memory. This was the fastest. And then you had HBM, which we lamented was so slow. But in this lecture, HBM is going to be considered fast. Now we're going to think about the single node multi-GPU setting where the GPUs are going to be connected via NVLink and NVSwitch. And then finally, the multi-node, multi-GPU where we have to resort to InfiniBand and Ethernet depending on what network you have. Okay, so last week we talked about various tricks for reducing memory accesses, fusion and tiling, read into shared memory, do everything as much as you can, and then write it back out. And this week, we're going to talk about how you can reduce the amount of communication across GPUs by replicating and sharding appropriately. So why do you do multi-GPUs? The obvious answer is, well, you want to scale. But to put a finer point on it, there's really two reasons. One is that your parameters or activations or gradients and optimizer state don't fit on the HBM memory of a single GPU. So B200 has 192 gigabytes. If you're training a 1 trillion parameter model, that's not going to fit on a single GPU. And the other reason is that even if your model could fit on a single GPU, you might want to leverage more GPUs by splitting everything up to train faster. So sometimes there will be kind of some decisions to be made because you could fit everything on GPUs, but you have fewer cores. But if you spread out, then you're going to have to pay the communication bandwidth, right? So that's some calculation you're going to have to do to figure out how to parallelize. Okay, so just one note here is that so far this lecture is Python. You execute it, and you can just show everything. Now in this lecture, if you run this directly, it uses multiprocessing. But when I trace through it, I'm putting in some sort of like special single process mode. So if you want to see the standard out for this lecture, run in the multiprocessing setup, you can click here, and I'll show this as we go through the lecture. But just remember, as we step through this lecture, we're not actually doing multiprocessing because we're just stepping through single lines of code. Okay, so this lecture is going to include 2 parts. One is we're going to learn about the building blocks of distributed communication and computation, starting with the programming model, talk a little bit about the hardware, start to implement things in Torch, which you're going to do on your assignment 2. And then the second part is we're going to look at actual training. We're going to look at 3 types of parallelism, data parallelism, tensor parallelism, pipeline parallelism. Each is going to cut up our model in different ways. We're going to do this for MLPs rather than the full transformer, but it's really sort of the core computation is going to be shown here. Okay, so let's dive in. So the first thing to talk about is these things called collective operations. So collective operations are these primitives from distributed programming that go back to the 80s. So the idea of parallel programming is very old. It wasn't invented for LLM training. And it's still the case that these primitives are the ones that we use today. And here, collective just means that you're specifying a general communication pattern or a template across multiple devices, rather than managing point-to-point how this GPU is going to communicate with another GPU. And this is going to be much easier, and the system can do a lot more work for you. So this is a very tried and true interface for doing parallel programming. Okay, so the general setup is as follows. The terminology here is a little bit, I find it a little bit strange, but this is standard in parallel programming. The idea is that you have a bunch of ranks, where rank corresponds to a particular device. In our case, a GPU, could be a TPU. But the point is that you have, let's say, 4 ranks here. The world size corresponds to the number of devices. So the world size here is 4. Okay, so there's a few operations we're going to go through. Broadcast, scatter, gather, reduce, all gather, reduce, scatter, all reduce, and all to all. And each of these operations is going to specify how this set of ranks or devices is going to transfer some amount of data / compute with it to some other set of devices. So the first 3, broadcast, scatter, gather, reduce, are really just warm-ups, I would say. They allow you to get a sense of how these collective operations work, but they're not really going to be the ones that are driving most of the training. All gather, reduce, scatter, and all reduce are the ones that are going to show up again and again for distributed training of language models. And finally, all to all, I'll just mention here, which is important for MOEs, but we're not going to actually spend too much time on this lecture. Okay, so let's dive in with the simplest operation, which is broadcast. So in broadcasting, you have a rank 0. It could be any rank, but let's just say, for sake of picking one, rank 0 has some tensor, 0, 1, 2, 3, and it broadcasts it to all the ranks. So at the end of this operation, we have that each of the ranks has the same tensor on it. Okay, that should be pretty straightforward. And this, again, doesn't really show up in that kind of the core path of training. Generally, broadcasts are used for kind of initialization, where let's say you initialize a load an initial checkpoint, and then you want to broadcast it to all the ranks. So something that's done like once. Okay. So the second operation is a scatter. And a scatter basically says, I have a tensor at rank 0 whose is split up into the world size, and I'm going to basically scatter my tensor onto the other ranks. So rank 0 gets 0, the 0th component, rank 1 gets this, rank 2 gets this, and rank 3 gets that. Okay? So again, this is not directly used, but scatter is an important stepping stone to understand reduce scatter. So as the name implies, scatter just takes a big tensor at one place and spreads it out onto multiple places. And you can see how this might be helpful because you want all the GPUs you're scattering to do some local computation on the different parts. Okay, so the inverse of scatter is gather. So this should be very predictable. The input is you have a bunch of pieces, each of which reside on a particular rank. And then when you do gather, that's with respect to a particular rank, rank 0, it's going to just concatenate all the pieces together. Okay, again, gather isn't directly used, but it's going to be a stepping stone to understand all gather. So next is reduce. So those of you who do functional programming are probably familiar with what reduce is. It's exactly the same. The idea is that you start in the same starting point as a gather, and where the tensor is split up across multiple, well, you have some piece of data on each of the different ranks, and then you're going to apply your reduction operation to all of these and get that put that on rank 0. So in this case, if you do a reduction with sum, then you add these all up, you get 6. Okay, so you can think about gather as a reduction where the operation is concatenation, if you will. Okay, and of course reduce is important to understanding all reduce. Okay, so let me pause there. Those were just kind of the warm-ups, just in case people have any questions about what a collective operation is, broadcast, scatter, gather, reduce. Yeah.
Broadcasting NumPy, or is it?
So the question is this related to broadcasting in NumPy? I mean, I think it's the same, conceptually the same idea, where you have one thing that goes to many things. Like in NumPy, if you have a scalar, it gets broadcast to a tensor. But the instantiation, this is for collective communication, so it's a bit different. Okay, so let's move on to something more interesting. So all gather is what you do to, basically you perform gather to all ranks, not just rank 0. So remember what gather does? It basically takes all the different pieces and it just puts it on one rank, rank 0. And now all gather just does it for every single rank. Okay, that's what the all is for. All means do it for all the output to all the ranks, and gather is what you're doing to all the ranks. Okay, so this is going to come up a bunch. It's not important that you understand this statement precisely, but later we'll see that each rank holds part of the parameters, and then what you need to do is all gather the parameters to get the full parameters for the full forward pass. So in general, as we're doing training, we're going to see a lot of this gather to do something, and then scatter, and then gather and scatter again. Okay, so reduce scatter is performing reduce on each dimension, and then scattering, the results. Okay, so you have, let's say, you have 4 devices, and each of them has some vector. And so when we did a reduce before, we just had 0, 1, 2, 3, and that got reduced to 6. But now reduce scatter says that for each component of this tensor, I'm going to do a reduction, and then I'm going to put it on a different rank. So the first dimension, I'm going to add these up. I get 6. Now for the second dimension, I'm going to add these up. I get 10. For the third dimension, I'm going to process these. For the fourth dimension, I'm going to process those. Okay. Okay. So where this is going to show up, just as to foreshadow things, after the backward pass, when you sum what you're going to do is each GPU will be dealing with different data, right? And what you're doing is you need to sum all of the gradients from the different shards, and then you're going to redistribute this storage. Okay, and then finally, all reduce. If you understand all reduce gather and all gather, it's basically you do one and then you do the other. Okay, so what this does is reduce scatter, the same input as we had before, and remember in reduce scatter we had 6, 10, 14, and 18 sit on different ranks. And the all gather part of all reduce just puts them all on the same, everything on the same node. Okay, so all reduce is in some sense the easiest to understand. You have a bunch of tensors, you reduce, in this case sum, and then you replicate them on all of the nodes. Okay, so we're going to see this one actually first when we do data parallel, where we sum the gradients and then we replicate the full parameters. So that's where we're actually going to start. So maybe just focus your attention on all reduce. Later, we're going to see how to get to fancier things like 0 or FFCP, we need to break the all reduce into reduce, scatter, and all gather. Because then you can intervene and you can manage things a bit more. But for the basic version, all reduce is fine. Okay, finally, all to all. This one is in some ways the most general. You basically specify how each rank sends a particular message to another rank. And so here's a simple example where you have the same input as before. And what this is saying is that I want to send 0 to this element to rank 0. Meaning keep it myself. I'm going to send 1 to rank 1, 2 to rank 2, and 3 to rank 3. And then if I'm rank 1, I want to send 4 to rank 0, 5 to rank 1, 6 to rank 2, and 7 to rank 3. So basically the position here is going to denote which rank is going to be the ultimate destination. And so if you look at the output, what happens is that the first rank is going to receive everyone who sent everything in column 0, because all of these ranks are sending these things to rank 0. Similarly, for rank 1, all of the ranks are sending this column to rank 1, and so on and so forth. Okay, so this is going to be useful when for training MOEs. And the intuition here is that each rank has both a split of the data and also a subset of experts. And basically, the key idea of the MOE is that it's sort of dynamic routing. You have to look at your data to figure out which experts you need to route those activations to. So it ends up being a all-to-all communication. So if you look at, if everything were balanced, meaning that every rank sent the same number of bytes to every other rank, then all-to-all you can think about as essentially a transpose. If you think about this as a matrix, all you're doing is transposing that matrix. But in general, all-to-all also handles unbalanced splits. And I'm not showing this here, but you can configure it to send any number of bytes to any other another rank. But in general, you want the splits to be as balanced as possible. So remember Tatsu's MOE lecture where we had load balancing to make sure that things were as balanced as possible. So morally, the ideal goal is to have things all-to-all look kind of like this. Okay, so just to summarize, maybe a few helpful tips to remember the terminology, because I just went through like quite a few different operations. So reduce is, well, it's reduced. It performs on some sort of associative commutative operation. Could be sum, could be max, could be min. Scatter is the inverse of gather. Scatter distributes, gather centralizes, and all just means that the destination is all devices. So that explains all reduce and all gather. Okay, let me pause there to take any questions about collective communications. Yeah.
For operations such as like gather and reduce, where we basically teach all ranks to rank 0. Does that rank 0 have to be designated beforehand? Like, is it like a particular GPU every time, or can that rank 0 change?
Yeah. So the question is, when you do a gather or a reduce, the target where you write the output. Right now, I said rank 0. You'll see later in the code, you basically specify the GPU ID or the rank, and it goes there. So it doesn't have to be determined like way in advance, but it has to be determined basically when you execute the call. Cool. Anything else? Yeah.
These are just like conceptual building blocks, right? They're not like actually things that, like, are there like these the actual building blocks that we use?
Yeah, so the question is, are these just conceptual building blocks or are they code? So I'm showing these right now as just conceptual building blocks, but we'll very quickly see how these are implemented in code. Okay, so before getting into code, I want to talk a bit about the hardware, in particular how GPUs are connected, because we already know what's inside a GPU. So let's talk about networking in general. So this is kind of a very classic picture. You can tell from this very old-looking image that this is how computers generally work. So you have this server, and then you have a bunch of CPUs. There's a PCIe bus, which you connect things like your, or used to connect things like your mouse and keyboard, and then you have a bunch of GPUs sitting off of them, and you have some RAM, and then this computer is connected to Ethernet to another computer, and so on and so forth. Okay, so this is a particular setup. It's a particular topology. GPUs on the same node, you use PCIe to communicate, and GPUs on different nodes, you have to go all the way through Ethernet. Okay, so this is like if you bought your gaming GPU and you had hooked it up with your friend and it's like, I'm going to train some big model. That's what you would have to do. But if you're really serious about training, then things look more like this. This is the picture I showed in the very beginning, where you have the GPU and there's something called NVLink and NVSwitch and InfiniBand. So the typical setup is this, and these numbers, 8 is typical, but this 256 is kind of made up. So typically you have 8 GPUs per node, and these are connected via NVIDIA's NVLink to a switch. And just for kind of calibration, if you use NVLink 5, then you're getting 1.8 terabytes per second of total bandwidth. And remember, HBM was for B200 was 8 terabytes per second, so it's about 4x slower. So this is still pretty fast if you think about going between devices, but obviously not as fast as high bandwidth memory, which is much slower than shared memory or L1 cache. Okay, so basically NVLink connects to the switch, and which means that from a programming perspective, you can think about GPUs as connected to any other GPU, right? You go GPU to any other GPU, and the hardware takes care of transmitting that to the switch, and the switch routes it. Okay, so typically what you will also have is that at some point you you can't have NV switch and NV link, and you have to, because as your clusters, number of GPUs grows, then you're going to have to put these nodes into pods or which are connected by InfiniBand. And the way InfiniBand works is that now there's a bit, more. So now the GPU doesn't connect directly to the other GPU. It has to go through PCIe and goes through this kind of special InfiniBand cable. And you see that the speeds are much lower. And then finally, if you run out of InfiniBand and you have these like huge pods, then you need to connect them via Ethernet. And in Ethernet, you have to go through PCIe, and it actually goes through this CPU, which, as we'll see, is even slower. Okay, so it's kind of analogous to the kind of memory situation. The more nodes you have, then the slower it's going to be. You can't have like an NV switch handling like 100,000 GPUs. So one note is that this, I alluded to this bypassing the CPU, which is going to be an important thing from a hardware perspective. So if you have traditional Ethernet, what happens is that the GPU has to talk to the CPU to get its data copied. So it basically has to copy the data to this. The CPU has a kernel socket buffer. Here is kernel means, not the GPU kernel, but the CPU traditional notion of a kernel. And then it has to build some network packets, copy to the network interface, and then ship it over. So this generally introduces a lot of latency. And so there's this technology called Remote Direct Memory Access, RDMA, which allows a GPU to directly write or read from another GPU's memory without using the CPU at all. So obviously, if you're in NVLink land and NV switch land, then you have RDMA. InfiniBand also supports RDMA. So if you're connected via InfiniBand, then you can directly have GPUs connect to each other without access involving the CPU. But standard Ethernet does not. There's two notable advancements I will mention. Is that so NVIDIA has been really pushing the limits on what you can do with larger and larger pods. So they have, for basically the B200s and the B300s, they have something called NVL72, which means that they have these trays of 8 GPUs, but have 9 of them. And so basically, at the end of the day, you have 72 GPUs that are all kind of NV switched into one NVLink domain. And if you remember, the NVLink speeds are very fast, right? So normally, if you're mortal, you think, well, okay, I have 8 GPUs that are interlinked really fast, and then outside of that, then things get slowed down a lot. But if you have a lot of money, you can buy this really fancy hardware, and you can get really fast interconnects up to 72 GPUs. And the other thing I'll mention is that, I said standard Ethernet doesn't support RDMA, but there has been progress on the Ethernet front as well. So there's something called ROCE, RDMA over Converged Ethernet, where the Ethernet actually bypasses the CPU. And this is sort of their answer to InfiniBand. So InfiniBand generally is very expensive, as is a lot of NVIDIA products. But you can get pretty good performance by using RDMA over Converged Ethernet. And Meta had some papers showing that they were exploring this. So Llama may or may have been trained over Converged Ethernet. Okay, so that's just a kind of brief overview of what the hardware looks like. You have GPUs. They connect via NVLink to an NV switch over some domain, maybe 8, maybe 72, and then it's infinite band from there. And now let's talk about how do you program this. So at the very lowest level, there's something called the NVIDIA Collective Communications Library, NCCL or NCCL, which translates the collective operations, the all reduce, reduce, broadcast, into the actual low-level packets that are sent between GPUs. So what NCCL does is it when you use NCCL, it's basically like saying I want to all reduce, and then NCCL goes and figures out what is the topology of the hardware, figures out the path between different GPUs, and then it actually launches the GPU kernels to send and receive data. Because at the end of the day, remember everything that runs on a GPU is a kernel, so there are communication kernels as well that actually do communication with other GPUs. Okay, so we're not going to look too much more into NCCL, but just know that it exists. And then we're going to actually go to PyTorch. So maybe before that, any questions about hardware? Yeah.
Can you describe? Does it be like a rack and tray?
Can I describe physically a rack and a tray, like what a rack is and what a tray is? So for the NV72, so I'm not a hardware expert, but a rack, is literally you've seen data centers, like literally a rack, and each tray is something that has the G stands for Grace, so there's 2 CPUs, and each CPU is connected to 4 GPUs, so each tray has 8 GPUs on it, and they're stacked, and everything is connected to this NV's switch. Yeah.
Also, describe the relationship between
Yeah, so the question is, what is the difference between RDMA is? Yeah, so RDMA, you can think about it as more of a desiderata. RDMA means that one GPU can read and write from another GPU's memory, and there's multiple ways to do RDMA. One is to use NVLink and NVSwitch, and another way is to use infinite band. So the infinite band and NVSwitch and NVLink are more the hardware, like what pieces, like what cables are and switch are there, and RDMA is more operation, like what happens when you're communicating.
So always switch really depend on internet, just like one way that the architecture. Yeah. So there will be other ways that each not switch, not
Yeah. For example, this advancement, RDMA over converged Ethernet is another way to do RDMA.
Okay, so if we would draw diagrams with this ROC and how we put it in like a diagram,
Okay. Yeah.
Is NCCL optimized for multi-node clusters? Because obviously, it seems intuitive for NVLink, but for RDMA-based processes, would NCCL be optimal for that?
So the question is NCCL optimized for multi-node clusters? So I don't know the details of how they have or have not optimized it. All I can say is that NVIDIA has been basically optimizing their entire stack for inference and training of these large models, because their main customers are the kind of major providers of language models. So I would be surprised if they haven't thought of optimizing for those type of workloads. Yeah.
What is the most common way you have workloads that you have 9 GPUs? Is there a most common thing to do?
So the question is, what happens if you have 9 GPUs? How do you distribute the workload across those? I suppose, I guess it kind of depends on how the 9 lands in your setup. For example, a lot of times you'll have, let's say you have 8 GPUs per node. So then the 9th one would be on a different node. And if you don't have, NVLink connecting them, then that's going to be really bad because that's going to be one node which is not providing that much compute and also very expensive to communicate with. But if you, let's say, had everything were connected by NV's switch, then it would be much more reasonable. Okay, one more question, I'm going to move on. Yeah.
GPUs?
So how is this different from TPUs? So Tatsu described TPUs a bit more. So let's see. What can I say quickly about this? So TPUs are generally kind of much simpler objects. I'm not too familiar with the details of how this, what each of these components corresponds to, but maybe we can talk about it offline. Okay, so let's actually get down to some code to take advantage of this hardware. So PyTorch conveniently has a torch.distributed library that provides a clean interface into these collective operations. So you don't have to explicitly think about nickel. And in fact, this library also supports different backends for different hardware. So if you are on GPUs, then you would use the nickel backend. And if you're on CPUs, then there's something called glue, which still allows you to, like I said, parallel processing has been around for a long time before GPUs, and you can do these collective operations on CPUs as well. This library also supports higher level models and algorithms such as SFTP, but we're not going to use those in the course because we're building things from scratch. All right, so let's walk through some basic examples of collective operations. So there's this function called spawn, which takes another function I'm going to call, and it says, I'm going to run this replicated 4 times, where 4 is the world size. So let's see what this does. This is actually a wrapper I wrote just to sort of hack around the fact that I can't do multi-processing in this lecture. So normally, what you would do is you call torches multiprocessing.spawn, and you call the function. But I'm going to do this branch which disables distributed. So let's just go through that. So now I'm in this function that it's supposed to be running on asynchronously for each process. So remember, world size is the number of processes, and the rank is either 0 or 1 or 2 all the way up to world size -1. And so there are world size number of these functions that are each running on a process at the same time. Okay, so I'm on rank 0 right now. So what do? There's a setup. You basically configure the master address and port. Notice that this is not actually how the GPUs are going to communicate. This is more for just general metadata and coordination. The actual data goes through nickel, otherwise it'll be very, very slow. And if you have CUDA available, then you can use the nickel backend. I'm on my laptop, so I'm going to use the glue backend. Okay, so now I'm here. I'm running. Pretend I have 4 of these processes running. So there's this barrier function, which is useful as it's a synchronization barrier. So basically, if I see this, then it waits for all the processes to get to this point. Okay, so basically, you can think about all the processes are running asynchronously. So I don't really control. One could completely finish before the other. They might be interleaved in any way. So if I want to make sure that there's some code that is executed before other code, I put these synchronization barriers in. So now the downside of putting more barriers in is that, well, you end up kind of waiting potentially unnecessarily. Okay, so let's try an all reduce. Okay, so I'm going to create this tensor 0, 1, 2, 3, and I have my rank just to make it more interesting. Each rank is going to have a different tensor. I'm going to print out what I have before the all reduce. So now I'm going to skip over here and see what gets printed out. Rank 0 before all reduce has 0, 1, 2, 3. Rank 1 has 1, 2, 3, 4, and so on. It's the same example as I showed before. Notice that the print statements are coming in whatever order the hardware feels like it because it's running async, but all the data is there. Okay. So now if I do an all reduce, and this, you pass in, this is a PyTorch function, it passes in this tensor, you pass in the reduction operation, which is a sum, and I'm going to say don't do async. And what this does is it calls, in this case it would be glue, but it could be nickel, and in which case it would spin up the CUDA kernels, it would do the communication, it takes care of everything for you, and then it basically writes in place to the data. So after the all reduce, I have the all reduce operation, remember, which is the sum of each of these columns, but replicated across all the ranks. Okay, so that's all reduce, and if you wanted to be fancier and do async, then you could say async equals true, but then it would screw up all these print statements. So I'm trying to put more barriers than I would normally would. Yeah, question.
In this case, the rank is for the other
So the question is the rank of the GPU. For this class, the rank is the GPU. Yes. Okay, so let's try another example here. So I'm going to do a reduce scatter. So here, I'm going to create an input which is 0 through the world size, and I'm going to have the output. I'm going to allocate the output. And so what does this look like before I do the reduce scatter? It looks like, let's see, this, where it's kind of the same input, and the output happens to be zeros, but it could be just anything. And then I do the reduce scatter tensor. Here, instead of writing in place, I have an output tensor and an input tensor. I say I want to do the sum. And then afterwards, I get basically the input is not touched, but the output, I get the reduction of each component written into the respective ranks. Okay, so yeah, question. Yeah, so the question is, how does it work to do the all reduces asynchronous? So what this means is that this is sort of like a monolithic operation. You say, go do the all reduce, and it's spinning up, CUDA kernels. It's going to, do the communication, and remember, CUDA is already kind of async with respect to the processes, and now we have all the processes being async. And the point is that this code just would return, and then you could do kind of other things. So a typical thing, which I'm not going to have talk about this class, is overlapping computation and communication. So for example, you can do this operation, and then you can go ahead and load some other data for the next step, which is independent of this operation. And then when you want to make sure that you actually are done, then you can call a weight or a barrier. Okay, so let's do the final one, which is all gather. So by now, I think you kind of get the idea. Here I'm going to set as the input the output of the reduce scatter. I'm going to allocate an output. So before the all gather, it looks like this. I have my results from the reduced scatter here. The output is, it's just allocated. It happens to have some values in it, but don't worry about it. And then after I do the all gather into Tensor, and then I will have all the different inputs gathered onto all the different ranks. Okay, and you can see here that indeed proof via example that all reduce is equal to reduce scatter plus all gather. Okay, and then just to wrap things up, just as I started by a setup, then I clean up, which it's good practice to clean up. Okay, so that was your first example of a torch distributed program. Okay, so let's do some benchmarking. This will be quick since I want to actually move on to the part 2. So how fast does communication happen? So let's do an all reduce. So here I'm going to all reduce with 100 million elements, and oops. Okay, sorry, mess this up. Okay, so all reduce. So I'm going to create this tensor with this number of elements. And remember, just like before, when we do benchmarking, we warm up first. And here, I'm going to call the CUDA synchronize and also the barrier, just to make sure that, because there's 2 forms of asynchrony here, the CUDA kernels and the different processes, and just want to make sure everything is kind of not running and is done before I start the time. And then I'm going to do the all reduce, and then wait again with the synchronize and the barrier, and stop the time. Okay, so remember this is running for every single rank. So if I look at the output here, for rank 0, 2, 1, 3, I have a different time potentially because they're all different processes. Each of them is going to report a certain measurement. And if you want to report one number, you can take the average, for example. So now, one thing that is useful to do, which is analogous to when we were computing MFU, is to measure the effective bandwidth. And the idea here is that, well, this took 1.6 milliseconds. How much, is that good or bad? So to compute the effective bandwidth, what we're going to do is to compute essentially how many bytes were sent and should be sent kind of during this computation. And then if you divide by the total time, then you get the effective bandwidth. Okay, so the size of what I'm sending around is the size of each element times the number of elements. So that's basically the number of bytes of this data tensor. How many bytes get actually sent? So this needs some unpacking. So for all reduce, if you think about, let's just say for simplicity, you do rank 0 plus rank 1 plus rank 2 plus rank 3. You need to iterate this world size minus 1 steps because there's a world size minus 1 addition operations. So that's this factor. there's a 2 because you need to both kind of send and reduce. So, and then you multiply by the size of the payload. So that's the total number of sent bytes. And the total duration is the time that, the wall clock time that it took, and then you multiply by the world size because it's like the total amount that all the ranks have waited. And the bandwidth is the bytes sent divided by the total duration. Okay, so in this case, you get something like about 400 gigabytes per second. Okay, so a few notes here. One is that the effective bandwidth, if you look at this expression, size times 2 times world size minus 1 divided by world size times duration. So as world size increases, this world size minus 1 divided by world size essentially converges to 1. So you're effectively left with 2 times the size bytes over the duration. So this is essentially the bandwidth. Notice that this is independent of the world size, which is good. So if you grow the number of GPUs you have, you are still, the bandwidth doesn't change. It is also independent of the topology, which is something that kind of Nickel figures out whether you're going to pass the messages in a kind of a ring or a tree topology. So yeah. Okay, so that is all reduce. And for reduce scatter, this is very similar. So I'm going to create the inputs and the outputs, warm up, perform the operation, and time it. So notice that the reduce scatter has these timings. And you can also measure the effective bandwidth here, the number of bytes that were in the input. You have the number of bytes that were sent. Here, there is no 2x here. And then the total duration, you divide by that, you get the bandwidth. So here, the bandwidth is, it should be very similar. I guess sometimes there's some stochasticity, but it's in the kind of 400s. So a few notes here. All reduce is, remember, as we stated, reduce, scatter, plus an all gather. And so all reduce naturally is moving twice the amount of data because reduce scatter has some cost, all gather has some cost, and all reduce is doing twice as much work. And it takes twice the amount of time, but the two cancel out, so you get the same kind of bandwidth. Okay. All right, so that is the end of part 1. Maybe any questions before I move to part 2?
Why did
Yeah.
you do that synchronize for the CUDA
So why do we have to do the synchronize for the CUDA kernel? So at the end of the day, we are still doing CUDA operations, right? We have just multiple processes, each with a GPU, doing some CUDA operations. And then, so if you're doing a CUDA operation, remember, by default, it's async. So when you reach the next line in Python, that CUDA operation might not be done. So we need to wait always until that's, to make sure it's done by synchronizing. Yeah.
So wouldn't you have to first do barrier and then synchronize? So the other way around?
So do you have to do barrier first and then synchronize? Not sure. Yeah.
I was thinking you want to do the first that all the devices read this line of code and then wait for all of them to complete it and then you do it. Yeah? And then you start your thinking?
Yeah, I think one problem is if you barrier first and then the CUDA might not be done running and you just immediately go to the barrier and then you are still kind of each independently synchronizing the different CUDA kernels, which means that you're not really synchronized. Like the barrier might, if all those operations just return, the barrier doesn't really do anything. Okay, let me move on. So now let's actually start thinking about how you train models. Okay, so we're just going to walk through a very bare bones implementation of training MLPs, multi-layer MLPs. I guess that's redundant. It's multi-layer perceptrons already. And remember that MLPs are the ones that are the actual compute bottleneck in a transformer, so this is actually pretty representative of what you'll see. Okay, so data parallelism, tensor parallelism, and pipeline parallelism. And the picture I want you to have in your head is this picture. So this is a little bit of a schematic, so don't think too deeply about this, but it's more of a way to conceptualize how you're cutting your data and parameters. So data parallelism says, I'm going to split the data into pieces, and then each of the GPUs is going to be responsible for part of the data, and I'm going to just do normal, I'm going to keep track of all the parameters and do normal model, training. And then I need to synchronize. So let me explain how this works. So I'm going to generate some sample data. So there's a batch size of 128, number of dimensions 1024. So this is a batch size by num_dim matrix, data matrix. And let's jump into this data parallelism. Okay, so the way that it's going to work is that you have this data matrix, and I'm going to break up the rows into a bunch of world size pieces, and in this case 4, and each rank is going to get a piece. Okay, so the number of dimensions, the batch size. So each, I'm going to call the local batch size basically, the batch size divided by the world size, which is every row is going to, that GPU sees is going to have 32, data points. And this is just indexing, start, index, data, start to end gets you the slice of that data. And I'm going to just put it on that rank. Okay, so at this point, each GPU has now a distinct data tensor, which is the part that they're responsible for. Now in practice, each rank should probably load its own data rather have this, this bottleneck, but this is just for illustrative purposes. Okay, so let's instantiate the MLP. So here I'm assume we have num layers, and num layers, and for each of the layers, I'm going to have just a num_dim by num_dim matrix. So I'm just going to initialize a random, set of parameters, and then I'm going to feed that into Optimizer. Okay, so here's the training loop. So in the forward pass, I take the data. So remember, data is not all the data. It's just if I'm rank 2, then I only get B2, part of the data. And I'm going to just go through the number of layers and do a forward pass. And then I'm going to do a backward pass. And then normally this would be it. But now remember, every rank has different data. Therefore, the gradients are going to be different as well. So this is the key step that makes data parallelism work. We're going to synchronize the gradients across all the workers. This is the only difference between standard training and DDP. It's actually pretty nice and elegant. So basically for all the parameters, I'm going to do an all reduce of param.grad. And I'm going to average. And then after this all reduce is done, then now at this point, each of the ranks has the exact same gradients. and then I'm just going to update the parameters. Okay? So it's kind of really kind of elegant, I find, because it's basically standard training where you apply it to your local batch, but you just insert this after the backward pass. Let's just average all the gradients via this all reduce. It's a one-line code change, and then the parameters get updated. So as you're training, each rank is basically performing parameter updates as if it had all the data on it, but it's only actually processing a part of the data. Okay, so that's basically DDP, or the first type of data parallel. Any questions about this? Yeah. So the question is, can you only do this with batch size greater than 1? Yes. So your batch size has to be at least world size for this to really make sense, and usually it should probably be quite a bit larger. Yeah. Yeah, so the question is, should the batch size be a multiple of world size? And that's also would be nice. Yes. I mean, if it's not, then you can pad it with zeros or something. So there's ways, but it's just easier for everyone if it is.
Can you talk about DDP for transformer? Like, what would it look like for a transform-based parallel?
Yeah, so the question is, what would this look like for a transformer? It would actually be basically the same. The DDP has a nice thing that is very modular. You do the forward pass. I mean, DDP just averages the parameters here. It doesn't care what your forward pass looks like. Okay, let me move on. Okay, so that's DDP. So just to summarize, the losses are different across the ranks. The gradients are also initially different, but they're all reduced to be the same across the ranks, and therefore the parameters all remain the same across ranks. Okay, so next lecture, Tatsu is going to talk about fancier data parallelism, FSDP and zero, and the idea there is, as I've alluded to, here we use all reduce. It's like a very simple monolithic operation, but it does require holding all the model's parameters in memory. But what if the model parameters don't fit in memory? Then you're going to have to be more clever, and that's the topic for next class. Okay, so let me talk about tensor parallelism. So here the idea is we're going to cut this way. I mean, we're not going to cut the data. We're going to cut essentially each layer. And so each rank is going to get part of each layer. Okay, and generally this means that we're going to have to transfer a lot more data. We'll discuss this a bit later. So what does tensor parallel look like? Okay, so we're just going to assume we have this data. Every rank has all the data, just for simplicity. And here, remember the data is batch size times num dim. And I'm going to define a local num dim to be for this rank. I only am responsible for a subset of the dimensions. So the picture here is that each model still has all the layers here for all the layers, but the parameters now are num dim times local num dim. Okay, so if this were one of the parameter matrices for one layer, I would be doing splitting down the columns. Okay, so this is also known as column tensor parallel. You can also do it by rows, but we're not going to talk about that right now. Okay, so now what does a forward pass look like? So go through all the layers, and I'm going to compute activations. So I start with x, the data, and I'm going to access the parameters at layer. And notice that this is only a slice of the parameters, right? So if I'm on rank 1, I only get this part of the matrix. But I can still proceed. I can apply this nonlinearity because this is element-wise anyway. But now, what I'm going to do is I'm going to communicate activations. So if I have a data matrix, rank 1 has activations for part of the activations for this part of the matrix. Rank 1 has part of the activations for this matrix, and so on and so forth. And I need to basically put all the activations on all the ranks. But we know how to do that. We introduced all gather as a collective primitive. So I have, this is all the activations. So this is the batch size times local num dim, which is the shape of the activations. And then I'm doing an all gather. So this is allocating memory for the activations. So X is the actual part of the activation. So this is batch size times local num dim. And all gather says each rank has X, and each rank is going to allocate activations, which is a list, one for each world size. And then after the all gather, X is going to be copied into each of the respective location activations. Okay, so then once I gather all the activations, I concatenate them to form the full dimensional X, which is batch size times num dim. Okay, any questions about column tensor parallel? So this is done for every layer. We now notice one difference between data parallel is now we have to kind of muck around with the model. Data parallel is very elegant because it's splitting by data. The model is treated as a module. But now we have to muck around with a model. And this is sort of strongly leveraging the fact that if you want to do a matrix multiplication, you can split it up into a set of smaller matrix multiplications. We can do those on different ranks, and then we can gather the results.
When it comes to the back propagation, it gets tricky, right? Because your gradients are still distributed.
Yeah, so now the question is what happens in backprop. Now in the backprop, you have your activations, and you have to reduce scatter to all the different gradients. So in some ways, all gather and reduce scatter have this kind of duality, where in forward, if you're all gathering, in the backward, you're reduced scattering. Yeah. So the question is that done automatically by autograd? So none of this, well, okay. So if you just call dot backward, it's not going to do it because there's no parallelism in that. But PyTorch has all these things that are done automatically for you. So.
So if I were to do the like, what would I have to add, or to what extent do I have to change my code, and to what extent is it just become that?
So in this, what is done for you and versus automatically? Here we're managing things fairly explicitly. So which means I'm not doing the backward pass, but you would have to manage and call the reduced scatter yourself.
Yeah.
And that's by design because this is 336, building language models from scratch. In practice, you probably wouldn't have to do that. Okay, so let's do pipeline parallelism quickly. So the idea behind pipeline parallelism is we're going to split the network this way. So each rank is going to get a subset of the layers now. within each layer, it's going to get all the dimensions, and it's also going to get all the, one of the ranks is going to get all the data. Every rank is going to see all the data in some form. So this is the way it's going to work. Okay, so let's, we have all the data, which is again the batch size times numdim. And I'm going to split up the layers. So local num layers is going to be the number of layers that a particular rank is going to handle. And so now I'm going to have local params, which is basically only there's local number of layers, number of them. But within each layer, I'm going to do the numdim by numdim. Okay, so one thing maybe Tatsu will talk more about this on Wednesday, is this idea of micro batches. So maybe I'll just present this and explain why I'm doing things this way. So in addition to splitting up the layers, I'm also going to split up the batch into a bunch of micro batches. So if I'm rank 0, then I get the data. And I'm going to chunk it up into a number of micro batches. And for each micro batch, what I'm going to do is receive it from the previous rank, and then do the feed forward pass only on the layers that are assigned to this rank, and then I'm going to send to the next rank. Okay, so here I'm actually using these receive and send, which are pointwise operations. So I didn't cover those before, but they're fairly explanatory. This basically says I'm rank, and I'm going to send this tensor over to, I'm going to receive this tensor from rank -1. And this says I'm going to send tensor x to rank +1. Okay, so basically the reason why I'm talking about micro batches is, and Tatsu will talk more about this on Wednesday, is that in pipeline parallelism, so you have one rank that gets the data, it processes some of the layers, and then it sends it to the next GPU, and it processes some of the layers, and it then sends it to the next GPU, right? So this is a very natural way of dividing a deep network. But the problem is that you get these what are called pipeline bubbles, where while you're not sort of processing, you're kind of waiting around for other tensors to process. And this ends up being quite inefficient. So the idea behind micro batches is that you break it up into smaller batches so you can kind of process it quickly, send it on to the next one. So this can reduce the number of pipeline bubbles. Okay, so the other thing I will mention that is not handled in this very kind of naive version is the idea of overlapping communication and computation, which is actually very important to pipeline parallelism. This basically gives you the right structure. If you put an I before these, then it becomes kind of async. You have to add more things to kind of manage the code. And the idea here is that you want to be, while you're computing here, you can be receiving data or sending data. So computation and communication should be overlapped, so that reduces the amount of time you're actually spent waiting. Okay, so a few things are kind of missing here, which we'll hopefully fill in next time. So the communication versus computation overlap, which is especially crucial in pipeline parallelism. I didn't mention in data parallelism, this also happens because I just did a forward pass, and then at the end I'm just doing all these all reduces. But if you're clever, then on the backward pass, as soon as the gradients are done, you can start sending that. And that's something you're being explored in the assignment 2. And this again allows you to just overlap communication and computation more. We had some questions about what about general models. Again, I think this MLP gives you essentially all you most of kind of what you need for understanding the basics. Some of the larger models just require a lot more bookkeeping, so it's harder to kind of see the core algorithms. There are other types of parallelism that we haven't covered. So sequence parallelism takes a whole sequence and chops it up into pieces, and that allows you to parallelize attention computation. Expert parallelism, which allows you to parallelize the experts for MOEs, and this is where the all-to-all that I mentioned comes in. And then also, different combinations of different parallelization techniques, which also will show up in the assignment. So one thing to note is that which parallelism technique you choose is going to be strongly dependent on the hardware. For example, tensor parallelism, there's a lot of communication because for every layer you need to send all these activations which are fairly big. So generally tensor parallelism happens within a node on NVLink or where you have high bandwidth. Whereas you wouldn't do tensor parallelism past the kind of an NVLink domain. Whereas pipeline parallelism, you'll see people using it, and generally this can tolerate much slower interconnects. So some of the decentralized training work uses pipeline parallel because your nodes or GPUs are actually halfway across the world. But you wouldn't want to do tensor parallel in that setting. So sometimes when you look at these combinations, it will be tensor parallel within a node, and then pipe data parallel or FSDP, and then pipeline parallelism if you need it. There's other effects such as if you do data parallel, you might be able to do data parallel quite a bit, but then you start hitting to something called the critical batch size, where if you start increasing the batch size too much, it doesn't actually help you, in which case you're just kind of wasting your compute, and then you're better off using tensor parallel. So there's a bunch of these considerations which we'll talk more about as we go through the class. So final note, so TPUs kind of came up a little bit. One thing to note is that on purpose, we are using PyTorch, and not just using PyTorch, but really using the collective operations in a very primitive way, so you can see mechanically what's happening. Another approach, especially if you're in your Jackson TPU land, is that you can simply define the model and the sharding strategy, and the compiler actually handles a lot of the decision of how to basically what kind of communicated operations you need. You basically say, well, this piece of data needs to be here and here and here, and then the compiler does some magic to figure out what. So that's appealing, but obviously it would take a lot of the joy out of actually building things from scratch. Okay, just to summarize, so there's many ways to parallelize. You can cut by data, cut by tensor or expert, cut by pipeline or sequence. We looked at data parallelism. We only did DDP. Next time we'll do FSDP and 0. Tensor parallelism, as I mentioned, requires very fast interconnects. Pipeline, less so. But you need to really work hard to reduce these pipeline bubbles. And then maybe at a high level, we see this kind of pattern come up a lot, right? So you can either recompute or store in memory when we were talking about things like activation checkpointing or doing, when we're working with GPUs. Or in this case, you can think about an extension of this is that you can store on a different GPU, right? From that perspective, you look at the data parallel, right? You're doing redundant work in some sense because every rank is actually updating its parameters and keeping track of all the parameters. But the reason you're doing that is that you don't have to move the optimizer state across. So one thing is that hardware is getting faster, but in some sense we'll always want bigger models. So this idea of having a hierarchical structure will always be there. Okay, so that's it for today. So next Wednesday, Tatsu will do more of a deep dive on more parallelism techniques.